Okay, so you guys got negative 1234.7. I kind of want to remind you of the heating curves that you saw in Chem 1. Remember when we had energy was on the y-axis, and you started in one place, you went up, and then depending on whether your reaction was endo or exothermic, told you where you ended. In this case, it's negative, so it is exothermic. And so it would kind of go down like this. Does that make sense? Yes? Okay. And this, the difference between the reactants and the products here would be delta H. In this case, that would be this number, negative 1234.7. Okay? And it's kind of like the, no, I'm not going to say that. Okay? Really, I would say these would be the energy to break the bonds in the reactants. That's if we were using bond association energy like we did a few weeks ago. And this would be the energy when the bonds are formed. Okay? But the delta H is when you have the difference here. By the way, what is this difference? Right, this is E sub A, which is activation energy. And does the burning of ethanol require any activation energy? Do you have ethanol? You probably have ethanol in the cabinets, in your medicine cabinets. You might have ethanol in your kitchen cabinets. Okay? Does it just burst into flames by itself? You have to get it started. Once you get it started, it will continue to react. But that spark, right, that initial match, that would be your activation energy. Okay, so now to tackle the other part of the problem, okay? You were asked, let me look at the basic question. Weren't you asked how many grams of water? Of the gas. Okay, so we're going to change this question. We're going to ask how many grams of ethanol would you have to burn, right? Okay, how many grams of ethanol needed to burn to heat, let's say, 10 grams of water from negative 5 degrees Celsius to 85 degrees Celsius. Cool? That's going to be our new question. Very, very similar to what you had in WebAssign. It'll give you a model. Okay? Now, so what we've done is we've figured out that when we burn this, we get negative 1234.7. How much of this do we have to burn in order to get all of this heat? A mole. So this is in terms of a mole, and that's why we just kind of assumed 2 moles, 3 moles, etc. Do you always burn a perfect mole? No. Okay, we just burn what we've got. Okay, so you can burn like 20 grams, whatever. So you can easily convert that to moles. And it might be a fraction, might be a half a mole, might be 0.37 of a mole, but we can figure that out. Okay? Now, the second part of the problem is it's going to involve us using our heating curves. We heat up, we melt, we heat up, we vaporize, and perhaps we heat up. Okay? What formula, this is melting, this is boiling. What heats do we use in these processes? What do we call this one? The heat needed to boil. Heat of vaporization. And what do we call this one?
Fusion.
Heat of fusion. And I wish they would call it heat of melting, because that's what it is. Okay? What do we use here on these diagonals? Pardon? You said specific heat? You're right, we use specific heat. And this is temperature. And what is the formula for heat on the diagonal? It's the one where we kind of had this silly song. It's the MCAT or the MC delta T. Okay. And then here, notice, would we use a delta T in our formulas here?
No.
No, because what's happening to the temperature?
Same.
Staying the same. And so if you were to plug in a 0 here, you would say it takes absolutely no heat to melt or to boil. And does that make sense?
No.
No. So what kind of formula do we use when we're melting or boiling or doing any kind of phase change? You guys know? Good. We're simply going to take the mass times the heat of vaporization or fusion, whichever one we're using. Okay, now, I just want to talk in general real quick before we get into the real detail of the problem. Let's talk about this heat of vaporization. If we're going to take mass times heat of vaporization, what kind of value are we going to have for heat of vaporization? What goes on top? Yeah, it's some type of heat. And what goes on the bottom? Some type of amount. Okay? Now, Anish says maybe that would be joules per gram. Would that work for heat of vaporization? Sure. Okay? Do you think you would always use heat? Always use joules? Is there something else you could use? Calories. It could be calories per gram. It could be kilojoules per gram. It could be kilocalories per gram. Do not let differences in units throw you off. What could we use besides grams? Moles. Okay? And I think like kilojoules per mole might have been what was in your book. Was it?
Yeah. What the hell I want.
Okay? And then you could have calories per mole. Okay? So again, usually if you're given calories, maybe you'll just continue to work in calories, or you need to look up a conversion. Don't let it freak you out. What's the conversion between a joule and a calorie? Anybody know?
Nope.
So like 1 to
4.18 joules is the same as 1 calorie. And you can look that up. You're really not expected to memorize that. That's nothing you would ever have to memorize.
Yeah, but can you just tell that because if you have specific heat of water?
If you have memorized the specific heat of water, yes, because the specific heat of water is 1 calorie per gram degree Celsius or 4.18. Yeah, that's kind of how I know it, Camden. Okay? All right. The other thing is, let's look at specific heat. Specific heat is a heat not only per an amount, but also per what? A change in temperature. Now, Abel, I'm going to go where you're going in just a second, okay? I want to make sure that you guys don't get freaked out about the temperature scale, okay? We tend not to use Fahrenheit. If you see Fahrenheit, just moan and groan and look up the conversion between Celsius and Fahrenheit and just do the math, okay? But typically, I'm never going to give you a Fahrenheit temperature. But I could give you a Celsius. I want you to think about this real quick. Let's say you had a problem where you had to go from 100 degrees Celsius to 200 degrees Celsius. What is the delta T there? 100 degrees Celsius, right? That's pretty easy, okay? Look at this. If I wanted to convert this to Kelvin, don't I just add 273? Okay, so 100 Celsius in Kelvin would be 373 Kelvin, and 200, wouldn't that be 473 Kelvin?
Yes.
Okay, let me ask you again. What is delta T in kelvins? 100. And we don't say degrees Kelvin, we just call it Kelvin. For that reason, guys, it does not matter whether you work in Celsius or Kelvin for delta T. Because it's a delta T, when you subtract them, you'll get the same value. A change in Celsius is the same as a change in Kelvin. So I don't even care if it's per Kelvin. You can pretend it's per Celsius. Don't let that trip you up. Okay? All right, Miranda, take it.